Hello, I'm John Gertz. I'm your friendly SETI theorist, and today I want to talk about the common or standard SETI strategy or protocol, which is to aim our biggest telescopes towards individual stars one by one in the hope that they are transmitting to us, broadcasting to us, sending us signals in somewhere in the electromagnetic spectrum, probably radio or usually radio or optical signals is what we look for. I don't think that's a good strategy. For the reasons I've earlier stated, I think that ET's better strategy is to send probes to our solar system. But I want to get a little bit deeper into the question of just why it is I've come to the conclusion that that's a poor strategy, to look for this type of remote signal sent from a faraway star as opposed to looking within our own solar system for probes. So let's first look at this from ET's perspective. They probably know that Earth is a biological planet. They would know so because they had sent scouting probes throughout the galaxy over billions of years and determined long ago that Earth has biology. With telescopes a little bit more advanced than what we have now, although some of our telescopes like the James Webb Space Telescope are on the cusp of being able to achieve this, when an exoplanet transits its stars or goes right in front of the star, that starlight is filtered through the exoplanet's atmosphere, and the spectra that we take from the star now has embedded with it signals of the molecules that are in the atmosphere of the exoplanet. The same applies if they're looking at us, and our planet, Earth, transits our sun. If those spectra have an abundance of biologically indicative molecules, then they put us into the atlas of the Galactica, Encyclopedia Galactica as a biological planet, even though they won't know much more about us than that. So they know that we're biological, but they don't know when that biology might emerge as technologically competent enough to receive their signal. Maybe we know we're here about 4.5 billion years after the creation of the solar system that we became technologically competent. But maybe their models of intelligent life call for state that's kind of average, that the average time for a civilization to emerge is 4.5 billion years, plus or minus a billion years, which means to say that they've got to dedicate themselves 24/7 over 2 billion years from one side of their statistical average to the other. And that's a long wait, and a lot of expended energy on their part, and a lot of dedication to the expenditure of that energy for a response that may never come. Humanity may never emerge as a technological species. It may never aim its telescopes at ET's transmitters. It might all be an effort in futility. And I have to ask, just why would they do that? There's a further imbalance here. The Earth is the recipient of all the great wisdom and knowledge, or whatever it is that ET is transmitting to us. We get it all for free, with no guarantee that we're going to even send them our wisdom or science, even though theirs is much, to be sure, much more advanced. So, in addition to that, there's a different unfairness that we on Earth become technologically capable finally, after the billion years that they've been looking at us, or whatever the number is, of course. And we only have to point our receivers at ET for as long as it takes for us to discover them. Maybe, 100 years or something. As we are doing our SETI right now and going around from star to star to star, we'll blunder into them eventually. It may take us 100 years. That's not fair. We only have to, look for 100 years. We use virtually no energy to do the search, and they have to transmit at huge energy for 1 billion years. There's no fairness in that. If I were ET, from a business perspective, it makes a whole lot of better sense for them, if they're going to transmit from their home star system, to make the assumption that we've got the onus on us to build massive receivers rather than to build massive transmitters. Why? A transmitter costs all the energy. A simple analogy would be that a star that we look at with our naked eyes or a telescope puts out obviously humongous amounts of energy just for us to be able to receive that energy in our eyeballs. We, on the other hand, require next to no energy to receive that light. All we have to do is either point our eyeballs in that direction or point a telescope in that direction. The telescope might take a little bit of electricity to run some gears and the back end camera and so forth. That's about it. It's not fair to the star. Okay, but analogize this to ET. Why would it do this? And essentially, they would assume that they can transmit. If they have to transmit 24/7 to planet Earth, that they can do so with very low amounts of energy, and that the onus is on us to rather build humongous receivers that are way beyond what we have currently, because good trade has to be fair trade. And the only fairness in this would be that we have to build the large receivers and they build the more modest transmitters. Now, consequently, one of the possible solutions is that they are in fact transmitting, but our current generations of telescopes are way too feeble to be able to pick up their transmissions. The second reason that they're not transmitting is that they may know for a fact or may suspect that there are many bad actors in the galaxy. And to transmit from their own location is to give away their own location. It may be very dangerous to do that. So that in itself may preclude that as a strategy, a communication strategy. The next problem is, okay, I got to say this quietly, so pay attention, because I don't want to say this because we're all friends here. The dirty little secret in the standard SETI observing protocol or strategy is that while it's designed to detect an interstellar radio or optical signal, it has virtually no hope of actually being able to discern the message, much less decode a message embedded within that signal. Put in other terms, SETI is seeking to detect the carrier wave, but not realistically the embedded message. Put in yet other terms, SETI observations are designed to prove the existence of ET, but not to listen to what ET may actually have to say to us. The problem with radio SETI is that we integrate a signal over time. When we point a radio telescope at a given star, the stars broadcast radio weekly, but they broadcast broadband radio across all frequencies. We're looking for a signal in just one narrow frequency. We don't know which frequency, but we're looking for a frequency where there's a narrow signal. In order to find that signal, what we do is we integrate the signal over time. So we just let the signal build up over typically a minute to 10 minutes, something like of that order of magnitude. But the problem is that the message would be smeared out of that. We don't talk in 1 minute chunks. If you record everything I say right now and then play it back all together in 1 second, it's just going to be a roar of nothing. It's just one noise cancel on top of another noise. There's no possibility to then, if you take all my voice over a single minute, to hear what I've got said in that last minute. You'll just know that I said something. So this is the second problem the next problem in believing that ET is sending us signals from its own star and that we're going to find it by integrating it. Put in other terms, if ET was sending us their sitcom, their I Love Lucy, we might be able to, if the signal was strong enough, we might be able to detect that there's an artificial signal there. But the antenna or the telescope that we would need to actually see the episode would have to be about 10,000 times larger than to just know that there was something there that was intelligent. In the optical, obviously stars have light. I mean, we see their light. But that natural light is broad spectrum. But to see a laser in that light, we have to currently, using the telescopes that we're currently using, we would have to build up a spectra of that light over seconds or minutes. We would build up a spectra, and a laser, which is not broad-based or broad spectrum, but rather very narrow frequency, would stick out as a single dot in that smeared spectrum. We'd see a dot, but we wouldn't see a message. The dot may itself be comprised of billions or trillions, or whatever their bit rate is, of pulses, on-off pulses, or small frequency oscillations. Either way, all we see is the dot. Now, with lasers, you have another problem that they only work for a reasonably short distance, maybe 1,000 light years out of a galaxy that extends for 100,000 light years. What happens after that is that dust begins to degrade the signal. The analogy here is to, back in the days when you could smoke in a theater, maybe I'm old enough to remember that, I don't know. Anyway, when people could smoke while they're just sitting there watching a movie, and the projector would go through the smoke, and you can see the smoke lit up in the interim between the projector and the screen. You'd see a band of smoke, but there wasn't enough smoke to totally obscure the movie, obviously. But if the screen was not 100 feet from the projector, but a mile from the projector, and there was still people smoking all over the place in between, sooner or later you'd get to a distance where every single photon leaving the projector would bang into a particle of smoke, and by the time, so that the screen would end up being black. And that's the problem you have with interstellar lasers. Interstellar radio is also subject to a lot of smearing and scattering due to the inhomogeneity of in electron densities and turbulence in the interstellar medium. A lot of technical issues here, but the problem becomes that it's going to have to be cleaned up a whole lot, maybe impossibly garbled, depending on how much interstellar medium it had to transverse. Now back to lasers, they've got a problem of aiming. A laser at 1,000 light years can aim at Earth pretty accurately, except for one problem. 1,000 years later, Earth isn't in the same spot. So that laser, the operator of that laser, ET, has to point at wherever Earth is going to be 1,000 years hence. That is not necessarily predictable. There's a lot of chaos in our orbit as we, the Earth and the solar system, orbit the center of the galaxy. It's being tugged this way, that way, and the other way by every single other every piece of mass in the galaxy, because every piece of mass attracts every other piece of mass, and the result is a lot of chaos. So that the exact position of Earth 1,000 years hence may not be predictable at all, so that the laser may simply miss. Now, there's another problem with the paradigm. Most SETI observations use a single telescope. This is hardly what I would call best practices. It sets up all kinds of problems. any purported artificial signal coming from ET would immediately demand confirmation, lest it be regarded as a false positive caused by some sort of system glitch, a microwave oven nearby, a nearby cell phone tower, or frankly a hoax. What you need are two telescopes at a distance from one another looking at the same object. If they both see the same or detect the same signal, artificial signal, at the same exact moment, and the two telescopes are 1,000 miles apart or whatever, that becomes very compelling evidence. But now the way things are set up, if there is a signal detection, what we have to do is immediately, call up another telescope and get them to look at the same spot. The problem is ET may not be waiting around that long. And the problem gets worse in a second, but if you see if as an astronomer, I see a detection, I immediately call up the nearest telescopes I can see. But they may be busy, they may be doing something else, they may the object I'm looking at may be below their horizon. If it's an optical telescope, maybe it's a cloudy day over there. There are lots of problems that could, and if that ET signal is transient, it's just there for a few minutes, like the WOW signal was in 1977. If it's just there for a few seconds or a few minutes or whatever, we've lost it. And without confirmation, nobody's cracking open the bottle of champagne. It's lost. The problem becomes magnified greatly by the fact that maybe most SETI is conducted offline. You don't actually looking at the signals as they're being created or looking at the results of your observations in the moment. Some SETI observations do take place in the moment, but on balance, most of them take place offline. The data is collected, gathered, recorded, and analyzed later. Well, you better hope ET's really persistently signaling to Earth, because if later means that ET has gone away and looked somewhere else and pointed its transmitters somewhere else, we're out of luck. In summary, in my judgment, looking at stars for transmitters that are going from their star to our star, standard SETI observing protocol, is a fool's errand. However, there are two major exceptions to this. The first is looking at stars within the I Love Lucy protocol, okay? That means to say those star systems that have had enough time to receive our earliest television transmissions, to detect them, and have also had enough time to send us back a signal. Since that was the first transmissions, television transmissions, took place about 75 years ago. If you look at half of that, 37 and a half light years, that's the amount of time to go the signal to reach ET and come back. There are only about 750 stars that lie within this small radius. It's a tiny, 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 tiny number in a galaxy of hundreds of billions of stars. Nonetheless, those stars are interesting and they're worth looking at. Those few 750 stars that lie within this small radius, and that radius grows every year, is definitely worth looking at. They've detected us, and maybe they're saying something back to us. That's SETI worth doing. And doing a lot, by the way. We should be constantly looking at those same 750 stars, not just, as I believe most observations are, contain those stars on their long list, and they'll spend 10 minutes on them and presumably have already done it and thrown them in the trash can. No, go back and go back and go back and go back to those same stars. They are interesting. Now there's a second way that we can look at stars, and not just within our own solar system for probes, as I've previously argued. And And that is not to look for their signals to us, but to look at their transmissions to us as a tiny subcategory of potential, what is now normally called in the literature, technosignatures. Okay, because it's a good word, technosignatures. Those technosignatures might be anything about ET that is detectable, regardless of whether they are intending us to detect them. So in other words, with somewhat more advanced telescopes than we have today, we might be able to detect the city lights of nearby stars, planets that are inhabited. We might be able to detect the infrared waste heat thrown off by their artificial structures that are orbiting their stars, such as big power plants or housing for huge populations of their beings. We might be able to detect nuclear waste products that have been dumped into their stars, the gamma ray contrails of their nuclear powered spacecraft, their radar systems, the odd shapes of megastructures as seen from Earth as they transit in front of their suns, planets that suddenly disappear because they may have been destroyed by warfare or by probes or whatever. Now, this is SETI that's actually really worth doing, albeit a lot of it is going to have to await more advanced astronomical tools that are currently available to us. What makes I should add that we may be able to detect in their atmospheres, artificial chemicals, or not just oxygen, which or other byproducts of biology that may be detectable, but artificial chemicals that clearly are not just biological but technological. What makes this kind of SETI so attractive is it doesn't require ET to give a damn about us. It doesn't require that ET know about us, care about us, is transmitting to us, or anything else. It just matters that they're detectable by any means whatsoever. So this search for technosignatures is really something that can be at hand right now. One of the great things that we are blessed with as an opportunity to look for technosignatures is that we are sitting on massive astronomical databases. This is the golden age of massive astronomical databases, and it's only going to grow larger over the next few years. We live in this age of databases. So we have sky surveys that are from Gaia, WISE, Sloan Digital Sky Survey, Kepler, the Vera Rubin survey, the LSST, the SKA, planetary data systems, and on and on and on. There are these massive databases that they either exist now or will in our very near future, and no human being can possibly look at it all. But machines can, and machines can be trained, or computers can be trained to simply look for the anomalous, for anything that doesn't fit, and that may turn up a technosignature. Thank you for watching today. I'm John Gertz, SETI theorist. These lectures are thumbnails of the ideas I've developed in a series of papers that have been peer-reviewed and published, that you can find links to them on my website, or you can wait until my book comes out. Now it seems in early 2025 with Oxford University Press, entitled Reinventing SETI. I look forward to seeing you next time. Thank you.